There we go. And now I'm back live once again. I gotta update that thing. Yay. All right. We have 2 weeks and a day until your AP test. 2 weeks and a day. It's going to go by very quickly. The month of May in general is just going to go by very quickly, but that's neither here nor there. My goal for today is kind of strictly twofold. Number one, as I stated in that homework assignment, I wanted to review some of the questions from that chi-squared homework that I assigned you, the thing that was due today. I wanted to review that in preparation, specifically for an assessment that I'm going to be giving probably later today or tomorrow or something along those lines. But I'm going to be giving an assessment on chi-squared testing, just because, well, we need to get that assessment in. But that's my first thing that I would like to focus on today. I would like to focus on going over questions specifically from that homework, and that would be absolutely phenomenal. After that, we begin the 2-week journey reviewing for this AP test. I'm going to be focusing on a variety of topics as the days go on to review. But today I'm focusing on a topic that, from what I can see from the past records that I have, that we kind of struggled on a bit. It would be the probability sections. So I do have a review set up for probability that I'm going to explain a little bit later that we're going to work on. And then I'm going to, I'll explain the details of that when the time comes. So in lieu of that, I would like to begin by focusing again on that chi-squared homework. So if you would, whatever work you have in regards to that chi-squared homework, you can break that out and kind of compare against what we're going to be doing. But like I said, I want to go over that. For those of you in the live chat, if you would, if you have not already left a comment, please make sure that you do so. Almost got him. Almost got him with the door. So, but yeah, leave a comment in the chat. That'd be absolutely fantastic. All right. Let me bring this thing up. No, that doesn't help. That helps. Pearson sign in. There we go. Stat book. I'm just bringing up my online stat book so I can zoom in on this thing if need be. There we go. Where in the world? What's going on with this thing? Hold on. There it is. That was weird. It was zoomed in way too much. There we go. And was it 663? What page was it that I gave you? 659? 693. I was way off. There we go. Excellent. Cool. Yeah, I probably should bring this up just so I can see the problem numbers. There we go. So you had numbers 6, 12, 22, 37, 54. 6, 12, 22, 37, 54. I just wrote those down separately. There we go. Okay, now there's no rhyme or reason as to where we should actually start with this information. So I'm just going to start with number 6. Here we go. I'm going to start with number 6. And then I may end up jumping around a little bit if you guys have a specific question. I may not be able to go over every single problem in this thing because I do have other things that I want to focus on during this class period, but I would like to go over a good deal of it. So focusing in on number 6 right there. There we go. Oh, sorry. Emails are popping up for my thing here. Here we go. Good. AP, there we go. A market researcher working for the bank in exercise 2 wants to know if the distribution of applications by card is the same for the past 3 mailings. She takes a random sample of 200 from each mailing and counts the number applying for silver, gold, and platinum. Now, to be honest, like I don't know how much experience you guys have with credit cards, like your own credit cards. You guys aren't even allowed to get your own credit cards, right? I have no idea. Shut up. Anyway, but it's just this general idea of people trying to get you to buy credit cards because they want you to buy stuff with them so they can charge you interest and blah, 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 blah. But they're basically, let's go back to the question. The researcher wants to know if the distribution of applications by card is the same for the past 3 mailings. This sounds like a test of homogeneity. This sounds like the type of test that we could type information into a matrix and be able to run the chi-squared test. Remember, you have a chi-squared test on the calculator. You don't have a chi-squared goodness of fit test. But when it comes to matrices like this, we could potentially do that, absolutely. They're not asking if 2 variables are independent of each other. They want to know if the distribution is the same for the past 3 mailings. Mailing 1 being what, 120, 50, 30, 115, 50, 35 for second one, 105, 55. I mean, they look pretty close, but let's kind of go through it a piece at a time here. What am I going to end up writing down for this? Well, they want to know what the null hypothesis is. Before I do any of that, I just want to get back to my calculator. Oh, not that calculator. There we go, that calculator. I want to type in this information. I want to see what the heck is going on with this thing first before I start writing anything down. So again, you'll have the TI 83s for the test at the very least, unless you have your own 84 and whatnot. You could hit second and then this button right here. Hey, what do you guys call that button? Like verbally, when you look at that button right there, what do you call it? Say again? Inverse? Okay. I mean, you could call it an inverse. I mean, some people call it x to the negative first, but like some people do call it an inverse. Just, whatever, regardless. I was just interested. But if you hit that button, second at that button, you'll come here to the matrices. You come over to the word edit, and you can enter in the matrix information. Now, let me jump to page 693 so I can enter in that information. So I don't have to keep flipping back and forth on the screen. There we go. You have a 3x3 matrix. Oh, 33. 3x3 matrix. You got to type in the size. I'm going to type in the information as is. 115, 50, 35, 105, 55, and 40. Double checking, making sure those numbers are typed in correctly. There we go. Okay. I'm just very interested as to what the heck is going to happen if I run this test. And then I'll go backtrack and write down a bunch of stuff. If I run this test, there we go, chi-squared test. Observed matrix is programmed in matrix A. The calculator will automatically do matrix B for me. And I'm going to calculate. If I calculate that sucker, okay, I mean, that will answer some of the later questions, but we'll talk about that. Oh, and they do degrees of freedom for me. Just kind of nice. If you remember degrees of freedom for the test of homogeneity, go back to the matrix. In this 3x3 matrix, it would be R minus 1 times C minus 1 to get the degrees of freedom. So it would be 2 times 2, which is 4, which is why they have degrees of freedom at 4. But that's neither here nor there. Here's the other thing we need to look at, though. When we run the test, we automatically get a matrix B. You can take a look at that matrix in 2 ways. Easiest way to do it is by going to edit and hitting matrix B, and you can actually see those numbers there. You would have to take a peek at the expected matrix because you would at some point have to talk about assumptions and conditions and the fact that the expected matrix, every cell is greater than or equal to 5. Which we have that information there. So let me actually do one more thing with this just because I want to see it. See what it looks like when it draws it. Holy crap. That thing. This is chapter 25. There we go. Well, again, it gives you the exact same information. It just gives you a visual as to what the heck is going on with this thing, which is nice, which is kind of nice. Okay. So going back to the questions themselves. trying to keep a page in this so I don't have to keep flipping back and forth. There we go. There all they go. What a morning. Okay. What is the null hypothesis? No, null hypothesis in this case is going to be written in words. I'm just going to jot out some information right here. There we go. For number 6, I'll have to zoom out. Null hypothesis, you can use the exact same notation of like h sub 0, but you're going to have to put this basically into words. Now, they're talking about whether or not the distribution, going back here, the distribution of applications by cards is the same for the past 3 mailings. Well, yeah, I could literally write that out in words. The null hypothesis is the distribution of applications by card is the same for the past 3 mailings. Yeah. We'll just do that real quick, see if I can shorthand it. The distribution of applications is the same for all 3 mailings. Let's just say. Show you what I wrote there. I just wanted to abbreviate a bunch of stuff. And then your alternate would be the distribution is not the same, or the distribution of applications is not the same. Is not the same. How can I not write that? For all 3 mailings. It may be possible that like 2 of them are the same, but that's not what this question is actually aiming for. Unfortunately, you're going to have to write that stuff out in words, but them's the breaks. There's other ways of wording that, but that's probably the simplest. What type of test is this? Now, I just mentioned that earlier. Yes, this is a chi-squared test, but you should specify that this is a chi-squared test of homogeneity. There are 3 types of chi-squared testing. There's chi-squared goodness of fit test. That is when you are comparing a generally accepted set of numbers versus an observed set of numbers. Let's say, like, what was the example that we did? Oh, yeah, we did the 1339 genetic theory for ears versus tongue rolls. Oh, 1339 is the generally accepted theory. Let's compare it against this actual class. Whereas in this example, in this matrix of information, this is all observed data. There's no generally accepted data, but they want to know whether or not the distributions are the same across that set of data. Well, yeah, if the distribution is the same, that's a test of homogeneity. If they're talking about whether or not the 2 variables are independent of each other, then that would be a chi-squared test of independence. It's run generally the same way as the homogeneity test. Just goes by a different name. What are the expected numbers for each cell if the null hypothesis is true? Again, this is where your calculator comes into play. If you ran that test in your calculator, and then you go to this matrix B, you can see those numbers floating around matrix B. Those are the expected values. Those are the expected values that you would write down. It's 113.33, 51.67, and 35 in every single row. But yeah, that would be the expected. The calculator will do that for you. You don't have to worry about calculating that by hand. You just have to make sure that you know how to access it in the calculator. The other way of doing that, I believe, if you go down to matrix B for names, yeah, it'll pop up like that, but it's a little bit more difficult to kind of see the data. You have to scroll to see the data at that point, especially if you have a bunch of decimals in there. My opinion, it's just a lot easier to just go over to edit matrix B. You see that stuff there. Let's see. Find the chi-squared statistic. We found that. We found the chi-squared statistic. The chi-squared statistic. If you run this chi-squared test right here, I'll just calculate it this time. Boom. 2.278. I'm actually going to write some of that information down here. Chi-squared is equal to 2.278. 781. I'll round it. And I'll even write down the p-value as well for later reference. There we go. Do they ask you degrees of freedom? Hold on. Scroll down. Oh, yeah, they do. Look at that. How many degrees of freedom does it have? Well, again, with the degrees of freedom, the calculator can tell you that information. There it is right there. Degrees of freedom are equal to 4. But if you were calculating degrees of freedom in this case, just for reference sake, number of rows minus 1 times number of columns minus 1. There are 3 rows and 3 columns. That's how they get degrees of freedom equal to 4. Zooming in on this, degrees of freedom, America. Let's see. Find the p-value. Well, yeah, we found the p-value right there. But let me also show you how to calculate the p-value using chi-squared CDF, just as a reminder. If I were to type this in, chi-squared CDF, 2.781, comma, some big number, comma, degrees of freedom. Yep, spits out the exact, well, the approximate p-value that we are looking for. It is important to know how that is calculated. You never know when that's going to come in handy. 0.595, obviously, but that's how it was calculated in that calculator. What do you conclude? Well, with a p-value that high, my immediate broad reaction is to fail to reject. You fail to reject because it is way too high. It is much, much higher than 0.05. But now we have to put things into the context of the problem. Always put things into the context of the problem. In this problem, they were trying to determine whether or not the distribution by card is the same, or the distribution of applications by card is the same for the past 3 mailings. Well, if we're failing to reject this null hypothesis right here, then I'm saying, well, I failed to reject the null hypothesis. The p-value is way too high, greater than 0.05. There is not enough evidence to suggest that the distribution of applications, there's not enough evidence to show that it isn't the same for all 3 mailings. In fact, you could say that there is evidence showing that the distribution of applications is the same for all 3 mailings. Just make sure that you use that fluffy language. Do not make definitive statements. There is evidence to suggest it appears. The data appears to be showing this. Things along those lines. Do not make any hard commitments on those statements. Okay. There were 4 other questions, obviously, that you had to do on this homework. Was there any one question of those 4, and it was numbers 12, 22, 37, 54, were there any of those 4 questions where you're just like, please help, oh God, help, help, please help? Yes. 37. Let me take a look. And let me zoom out. 37. There it is. Haha. I tried giving you guys a lot of Titanic stuff. I don't know why. Did anyone see the movie after our conversation about it? No? Goodness gracious. I teach a cryptology class where literally every movie I watch, like a couple of kids in the class go home and watch it like that day. Just saying. Anyway, back to this. Oh, here's the table we first saw in chapter 2, showing who survived the sinking of the Titanic based on whether they were crew, passenger, booked in first, second, or third class. Yes, it's the same numbers. All right. If we draw an individual at random, what's the probability that we will draw a member of the crew? Now, yes, you are going to get more practice with probability today, but some of these did start out just being probability. In fact, it's a bunch of probability problems until finally they get to the null and alternate hypotheses. But if you draw an individual at random, what's the probability that they're a member of the crew? Some of these problems should be fairly straightforward. I'm just going to write something up here real quick. There are 885 people in the crew. It's a general question about the entire thing, so it's out of 2201. It's not talking about alive or dead. It's just drawing an individual at random. It didn't specify if they're alive or dead. So it would be this calculation right here, 885 out of 2201. Whatever that decimal would end up being. Hold on. 885 divided by 2201. Yeah. About 0.402. Something like that. 0.402. Yep, there it is. But then the next question, what is the probability of randomly selecting a third-class passenger who survived? Now, all of a sudden, we're talking about conditional probability. Now we're talking about conditional probability. The probability of selecting a third-class passenger given that they survived. So given that they survived, given the survival category, means that I'm probably just looking at those numbers right there. Third-class passenger, 178 out of 710. I'm going to double check that. Make sure that that number worked out the way it was supposed to. 178 divided by 710. Boom, 0.251. Oh, it's wrong? How is it wrong? No, the book is wrong. No, I'm probably wrong. Anybody get a different answer for that? I got 0.251, and I'm fairly certain that I'm wrong. Anybody get a different answer? What'd you get? Say again? Okay, so like 8.1%. And somebody was about to say another number. Same number. What did you do to calculate that? Let's see how I was wrong. Interesting. The wording of the question foiled me again. The wording of this question, I interpreted it as conditional probability. But the way that you interpreted it is the way the book says it's correct. The way that, all right, I'll write this up here. You'll see exactly what I'm referring to when I write it out. The way that I interpreted this question was the probability of a third-class passenger given that they were alive. And the way that I calculated that was 178 out of 710. But the way that you just verbalized it to me, you calculated third-class passenger and alive. Which, I'm sorry, give me the numbers one more time. That's what you did, yes. Out of the whole thing. That who survived thing, that's what's breaking my head right now. I assumed that this was a given probability. Goodness gracious. What is the probability that randomly selecting a third-class passenger who survived? Goodness. Oh, that's one wrong from me on the AP test. But yeah, no, the book is saying that your calculation was correct. I don't like that question, but I accept my defeat. Part C. Oh, which, by the way, again, this one is the one that the book says is correct. I would continue arguing the book, but I don't think I can right now. I'm defeated. Part C. What is the probability of a randomly selected passenger surviving? Okay, now they're really spelling it out for me. This is like a dummy question for me. What's the probability of a randomly selected passenger surviving given that the passenger was a first-class passenger? I'm pretty confident in this one. Clearly, since they're using the word given here. I know, right? Goodness gracious. What is probably the survivor? Okay, so first class passenger surviving 202 out of 325. Let me calculate that real quick, see if the book wants to confirm that I'm right. 202 divided by 325, 0.621. And yes, the book is confirming that that's correct. 202 out of 325 is about 0.621, or 0.622 technically it rounds to. Man, the wording of these questions. That's why probability messes a lot of people up. Because it's like, oh, it's math. Math is supposed to be concrete. It's like, yeah, well, could that question be interpreted differently? It could, I guess. Nah, not really, I guess. I don't know. Part D. If someone's chances were the same, regardless of their status on the ship, how many members of the crew would you expect to have lived? Ooh, now this is an interesting question. You can get the calculator to do this for you. You can get the calculator to do that for you. Write this thing down. Now, just for the sake of argument, I'm going to tell you what the book says, and then I'm going to try it on the calculator and see if it actually works the way that I think it does. The book says that the answer is 285.48. That's what the book says. I want to see if I can get the same answer doing what I'm about to do here. All I have to do first, I have to type in this information into the calculator. I'll show you what I'm doing in a moment. I just have to make sure that I'm typing in the numbers correctly. Cool. So 212, 202, 118, 178, 528, 167, 123. So, okay, cool. Click. There we go. Oh, it's frozen. My heart. Zooming in, zooming in, zooming in, zooming in, zooming in. There we go. So I typed in the Titanic numbers into the matrix function one more time. I made it a 2x4 row by column, and you can see all of that information typed in the way that it's supposed to. Now, when they're saying in the question, they're saying how many members of the crew would you expect to have lived? I'm going to force the calculator. I'm going to run a chi-squared test. I'm going to calculate it. Now, I don't really care about these numbers right now. Those numbers are not really of interest to me at the moment. But what I'm really interested in is matrix B. Because in matrix B, I could get that exact answer. Right there, 285.48. This is the expected matrix. And according to this, that would be the top left number would be alive and in the crew. The expected number of being alive and in the crew, 285.48. The rest of the numbers are just the expected numbers from everyone else. According to the question, if someone's chances of surviving were the same regardless of their status, if the distribution was the same across all the categories, how many members of the crew would you expect to have lived? That's how you can force the calculator to do it for you. I love it. State the null and alternative hypotheses. Well, according to part D, actually, let me read. Is there anything up here? Okay, yeah. According to part D, they're talking about independence. They're talking about independence here. So this is the chi-squared test of independence. So we have to reference that for the null and alternate hypotheses. If I'm going to be writing a null hypothesis for this, I would say that surviving on the Titanic, for the null, surviving on the Titanic is independent of, I don't want to say class, because it's like class and crew, I guess. What did they call that exactly? Yeah. So yeah, independent of whether you were on the crew or for first, second, or third class. I don't even know what to call that. You could even say just class. And then the alternate hypothesis would be that they are not independent. I mean, you could even say, yeah, it's dependent, but I prefer saying like not independent. Either way, it would have worked. Degrees of freedom, America. Well, with degrees of freedom, it's a 2x4. 2x4. Boom. Degrees of freedom are 3. Although I'm pretty sure the chi-square test would have told me that regardless. And then the chi-squared value for the table is 187.8. Hold on. Let me double check something here. 187.8. Yes, it is. It's just, it's right there, clearly. But they tell you that in the problem. The chi-squared value for the table is 187.8, and the corresponding p-value is barely greater than 0. Yes, that is true. 1.8 times 10 to the negative 40th power. That's essentially 0. State your conclusion about the hypotheses. Well, clearly your conclusion should be to reject. You should absolutely reject. Based on the p-value being essentially 0, this is technically what one could argue as like overwhelming evidence, something along those lines. This is like overwhelming evidence against the null hypothesis. This is overwhelming evidence against assuming that that your survival on the Titanic is independent of your class. One could argue that it's very close to being dependent, I guess you could say, to an argument. You could even, you could, as long as you stick with the fluffy language of like evidence to suggest, you could do something like that. You could say like, that there's, because the p-value is essentially 0, 1.8 times 10 to the negative 40th power. This is strong evidence against the null hypothesis. There is evidence to suggest that your survival on the Titanic is not independent of the class that you were in. You could even say that your survival on the Titanic is dependent on the class that you're in. But make sure evidence to suggest, it appears, the data implies, use that fluffy language. You take your pick on how you want to word that, being the wordsmiths that you are. Oh, the English language. Okay. I want to do at least one more. Did I give you another Titanic problem? Sweet. There we go. Should really watch Titanic, I'm just saying. It's a long movie. I don't know. Newspaper headlines at the time and traditional wisdom in the succeeding decades have held that women and children escaped the Titanic in greater proportions than men. Here's a summary of the relevant data. Do you think that survival was independent of whether the person was male or female? And then explain. Now, you can't just look at the data and just be like, yeah, well, just look at the data. No, you can't really do that. Clearly, if you look at the data, there were a lot less females, but proportionally, yes, a lot more females survived compared to the number of men that died. You figure out like proportions that way if you wanted to. But you cannot just say, look at the data, look at these proportions clearly, one over the other or something like that. You can't do that. Instead, you really should be running a hypothesis test. And because this data is arranged in a matrix, and because the question is asking whether or not survival was independent of whether the person was male or female, this is a chi-squared test of independence. So I'm going to go back to my calculator. Let me clear this thing out. There we go. Matrix, edit, 2 by 2. Let me enter in the data. 127, 1364. I'm just double checking all those numbers. There we go. That data is typed in appropriately. Stat, tests, chi-squared. Observed, expected is blank. It's going to recalculate it anyway. Calculate. Holy crap. That p-value is so stinking small, they don't even bother like giving you scientific notation. It's probably like times 10 to like the 120th or negative 120th power or some junk like that. So if you're going to be running something like this, make sure they don't give you any other information. But if you're going to go through the entire hypothesis test, you need to make sure that you hit every aspect of it. Write out your null and alternate hypotheses. Null being that, yes, survival was independent of whether the person was male or female. Alternate being survival was not independent of whether the person was male or female. One could argue dependent. Going through the assumptions and conditions, you definitely want to make sure that matrix B has at least 5 in each category, or each cell, I should say. And yes, it does. It's very important that if you're going to be doing a hypothesis test, that you write down the expected matrix. That would definitely be helpful. Now, in terms of the 10% rule, you're dealing with all of the people on the Titanic. That's going to be a little bit iffy. Like, how do you write out the 10% rule when you're dealing with people on the Titanic? Well, this is not a random sample. It's not a random sample, but you're running with the assumption that survival on the Titanic was independent of being male or female. This is the really iffy part about assumptions and conditions. Randomness really is there to point to independence because you need each person's survival and being male or female to be independent of each other. But in this test of independence, your null hypothesis is assuming independence at the beginning. That's the really iffy part. For randomness, you don't really have to speak to it. But independence, you definitely should make mention. Independence was assumed in the null hypothesis. Something along those lines would definitely be appropriate. Oh, this data stuff that they have thrown out here. Assumptions and conditions. But that's what the chi-square test is really doing. It's testing to see whether or not the data is independent. Oh, what am I flipping there for? The p-value is essentially 0. Report that chi-squared number as well. Since the p-value is essentially 0, is so low, less than 0.05, there's overwhelming evidence to reject the null hypothesis. There is strong evidence to suggest that survival on the Titanic was not independent of being male or female. One could argue being dependent on being male or female. I don't think it was a hard and fast rule that when a ship was going down, they had to say like men, women, and children first. I really don't. I really don't know. Do you know why so many people died on the Titanic, despite the fact that they had a bunch of those boats? They were not filling the boats to capacity. The first class passengers, like, they didn't want to be crowded on those boats. It's really weird. Such a weird world we live in. Anyway. Are there any other major questions from that particular homework that we can talk about before I say, well, it's submitted on Google Classroom, before I take a step in another direction? So I want to make sure that we hit that. Keep in mind that I am going to be assigning you an assessment on chi-squared either later today or tomorrow. Just a short assessment just to knock that thing out. And then we're going to begin reviewing everything else. Cool. Here's what I need you to do. If you do not already have them out, I'm going to need those Chromebooks out and open. Because I got something I need to test on you. Well, I shouldn't say test, because it's not a test. It's not an official test. So I don't know why I called it that. I need to see where you're at with something. The way that the next few weeks are going to work, is as I'm reviewing this information, I still need to put in grades. And in doing so, some of these things I'm going to have to assess you on are, well, parts of the review that we're going to be doing. But it's not fair for me to just be like, here's a review on something we haven't talked about in 6 months. Get graded on it. That's not really fair. So instead, I want to do something a little bit of an experimentish type thing today, where I want to throw quizzes at you. But with this quizzes, afterwards, I would like to review as much as we possibly can. So let me do that. So get on to that quizzes website while I get this thing started live. We'll just do it once to that thing, shuffle the questions. I don't want to put on redemption questions. Yeah, I'm turning off redemption questions. This is a review. This is a practice. I'm turning off redemption questions because I really want to get a pure idea as to whether or not you got it right or wrong the first time. There we go. I'm going to throw that thing right in there. There's that code. There we go. Oh, volume. Turn the volume down. There we go. As people are popping in there, obviously giving people the opportunity to get the things logged on and whatnot. Have those calculators ready to go as well for some of these problems, because some of these problems you may need a calculator to help you out. 751-250. Just making sure the code is in there for those who are in the live stream. There we go. Now, probability has been something that we haven't actually covered regular probability since like February, maybe, or something along those lines. So it's been a while. It's been a minute. But we need to be on top of this stuff as we move forward. We have about 2 weeks, and I want to start slowly kind of working our way into this stuff. And this is the first step in that direction. So give people a few more minutes to kind of get logged on. How many are here today? So I got 8. You got 12, 13, 14, 16. You got 16 in here. You got about, I think, 4 or 5 online. No, it says 8 online. Oh, my goodness. All right. If you haven't joined yet, the code should be at the top of the screen. If you're in the live chat, the code should be in the chat room. Or not even a chat room. Ugh, I don't even know what to call that. You guys don't even know what chat rooms are. So imagine this. Back in the day when the internet first became regular to the average person, I went over a friend's house and he logged on to the computer and he's on this website. Well, not even a website. It wasn't even a website. It was an interface called America Online, which I'm sure you've heard of, or something like that. And so he goes into this, like he clicks a couple buttons and he gets into a chat room that's talking about professional hockey. Because he was a hockey fan or something like that. And I'm like, I'm in 8th grade and I am like weirded out. I'm just like, so all these people talking right now in this chat room are from all over the world. And he's like, yeah. I'm like, so you could type in a sentence and somebody in like Texas could see it. And he's like, yeah. I'm like, that is cool. Like, you guys will never have that wonder. Anyway. The what? No. I hate Reddit. Goodness. Reddit's a cesspool. It really is. All right, let's get this thing started. Where's my mouse? There it is. Click. That's not us. I would recommend that if you are someone who has finished, because I know a handful of you have already done so already. I think you have the ability to look at the questions, like what you got right, what you got wrong at the bottom. Yeah. You should definitely take a look at some of that. Now, I may not go over all the questions that you got wrong, let's say, because clearly everyone's gotten at least one wrong on this. But I'm going to sort by accuracy. I'm going to be able to take a look at the ones that we struggled on the most as a class. For you guys that are still working, I'm going to give you another minute or so, and then I would like to start looking at the problems that we were the least accurate on. I also want to show you something in regards to an AP grade calculator based on the scores that we're kind of what I'm seeing right here. Here, there we go. There we go. Come on, yeah. Okay. I'm going to click to end this, and we got very close to 50-50. We're about 9 short of 50-50, but I'm going to end it right there with that one. I wanted to show you this first. Now, I've showed you this before. But I want to show it to you again. You can see right here where my mouse is kind of circling around. This is the AP grade that you would have gotten given the following on the actual AP test. Now, this is a hard test. It is. It just is. You just took multiple choice on probability. Obviously, probability is not going to be the only thing that's on there. Now, I actually lowered this to like a bare minimum right here. Look at this. I put this so this person only got 16 out of 40 correct on the multiple choice. That's 40%. 40% on the multiple choice. A 2 out of 4 on the first 3 questions. A 1 out of 4 on the last 3 questions on the free response. And this person still passed in 2016. It is a hard test. Now, obviously, year by year, it changes. Like if I go back to 2007 and I try to put in the same numbers, let's say. Let's see here. Calculate. 2007, you'd still pass. It's a hard test. So if you're looking at this multiple choice and you're like, oh, snap, I did not do so great. Well, this is a hard test. It's meant to be a hard test. I think like, hold on, let me go back here actually real quick. Where are you? Oh, there you are. I left you full. There we go. So if I go back to 2016 and let's say I changed it down to like, let's say you got 1s on all of this. 1s on every free response and 20 out of 40. You got half of the multiple choice correct. You still pass. It's a hard test. I tried going down lower. It was like, okay, what if you got 19? Oh, 19, then all of a sudden you don't pass. But let's say like you get like a 4 out of 4 on the first free response, a 3 out of 4 on the second one, and then you bomb the rest. I don't know, what could you get here? Oh, you can go down. I'll probably go down lower. Hold on. 14. Yep. 13. Yep. You can get a 33 on the multiple choice. Nail the first 2 free responses. Bomb the rest and still pass. It's a hard test. Your assumption is that everyone else is doing well. Do the best that you can. So let's take a look. Scrolling all the way down here. Oh, sweet. So these questions are all mixed up. This is number 22. I want to review some of the, I sorted by accuracy, but the least correct problem that we got. The toughest problem that we got was this one. Find the standard deviation of binomial distribution, round to the nearest tenth. Well, I'm going to type something into my calculator real quick, and I'm going to show you exactly what I typed in. There we go. And let me, wait, there we go. Come on, you. This is what I typed in. It's a binomial distribution. A binomial distribution has a standard deviation at the square root of NPQ. That is the formula that is given to you on the formula sheet. NPQ. They want you to round to the nearest tenth. You can see it right there. Question. 7 of you put 4.2. I think I know why, but I'm not certain. What formula did some of you end up using that you found, oh, that was an incorrect formula? If you want to volunteer that information, because I was trying to figure out how in the world did you get 4.2 from that? I'm thinking, did you do 50 times 0.4? No, that's 20. Clearly 20 wasn't the answer, and 20 wasn't one of the choices. Multiply that by 0.6, you get 12, which 12 was one of the choices. That's if you don't square root it. 0.4 times 0.6 divided by 50. Nope. 0.4 times 0.6 divided by 50. Square root of that answer gets you 0.7, but 0.7. I don't know. But it was that formula. It was the square root of NPQ. That was our toughest question. Take a look at this one. Oh, here we go. If you were to flip a coin 20 times, it's number 7. Number 7. If you were to flip a coin 20 times, what is the probability that you would get exactly 10 heads? A finite number of trials. There are a finite number of trials in which you are looking to get a certain number of successes, in which you are looking to get, well, not just a certain number, but exactly the right number of successes. This is a binomial problem, but more importantly, this is a binomial PDF problem because you're looking to get exactly that many successes. 20 trials, 10 successes. Looks like 0.177. Well, or 17.62%, yes. If you round that. Oh, not 7.7, it'd be 7.6, whatever. But still, that would be the answer right there. Let me see your calculators real quick. If you go to binomial PDF, yep, number of trials. It was a different interface. I just wanted to see what it looked like. 0.5, 10 successes. You do get that as an answer. Let me see what happens when you do CDF. CDF, 20 trials, 0.5, 10 successes. This is CDF, meaning 10 or less successes, 0.588, which was one of the choices, but only one of you picked it. 10 of you picked 50-50. 10 of you picked 50-50. Oh, yeah, because if you flip a coin, there's a 50-50 shot, but it's just a 50-50 shot on that flip. Getting exactly 10 heads? Well, I can see why you would automatically think 50-50, but this is a binomial problem. Each trial is independent of the next. Let's see where we go from here. Here we go. The probability that Jalen makes a free throw attempt, this is number 23. He makes a free throw attempt is 75%. Now that's an assumed independent probability. What is the probability that he makes the first free throw on the third attempt? Now, obviously, this is a geometric problem. Let me go to your calculators real quick. If you go to your calculator for geometric, which, hold on, let me read this one more time. He makes the first free throw on the third attempt. This is a geometric PDF problem. Getting it on exactly that trial. The probability of success is 0.75. Getting the success on the third shot. That is the order in which things need to be typed in. There's no set number of trials. There's no set number of trials, meaning there's no n value. But 0.75 is the probability of success, assumed to be independent from one shot to the next. 3 successes. Now, obviously, they didn't want that decimal. They wanted to know which one was the correct way to type it in. Geomet PDF, because you're getting it on exactly that third trial. And in that order, 0.75, comma 3. Yep, looks like 8 of you chose CDF. CDF would be getting that first free throw on the third attempt or sooner. CDF would be cumulative. Let's take a look at this one right here. Ho-ho! Okay. Ha-ha. Sorry. Look at the average time taken. I just thought that was interesting. 8 seconds. Find the variance of the binomial distribution with 50 trials and P being 0.4. What did everyone choose in 8 seconds? A bunch of you chose 20. Was that just because of 50 times 0.4? Yep. That was just because of 50 times 0.4. Move that there. There we go. But they want variance. Square root. 50 times 0.4 times 0.6. That's not variance. That is not variance. That is standard deviation. That's the square root NPQ formula that they give you on the formula sheet. Now, clearly, I could just do that calculation without square rooting it, or I could square it to get 12, which is the answer. 7 of you chose 20 right off the bat. I can see why you did that. 8 seconds. 8 seconds. That's interesting. Okay, here we go. Which, by the way, from what I'm seeing on here of probability, it seems like the toughest problems that we were faced with were were the binomial problems. So this is good insight for me to know what I need to be covering in part of the review. If a fair coin is tossed 200 times, what is the probability that at least 99, meaning 99 or more, but less than 110 turn up? I got to write something on the board for this. I think this will be the last problem we do today. Let's see. How many successes? Bum, 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 bum. 98, 99, 100, 101, 102, 103. Yeah. 104, 105, 106, 107, 108, 109, 110, 111, ... I'm doing this for a reason. At least 99, meaning 99 or more. I'm going to have to do that calculation at one point. But less than 110. If it just says less than 110, I would assume that they're not including 110. So it'd be that or less. So those are the calculations that I really need to be focusing on. This is a binomial problem. Now, if I do binom CDF 200, 0.5, 109, that will give me that calculation for 109 or less. But they only want 109 down to 99. So what I'm going to do a little bit of trickery here, because there's multiple ways of doing this problem, but I'm going to do a little bit of trickery here. And I'm going to do binom CDF 200, 0.5, 98. And what I'm going to do is I'm going to do that calculation, and then I'm going to do that calculation with 98, and then I'm going to subtract them and see if that works. Let's see if it does. There's more than one way to do this problem. There's definitely more than one way to do this problem. Just want to see if this works the way that I want it to. Binom CDF 200, 0.5, 109 minus, close the parentheses, of course, binom CDF 200, 0.5, 98. Boom. Get an answer of 0.4945, which is exactly what the correct answer should have been. There's more than one way to handle that problem. There's absolutely more than one way to handle that problem. But in my opinion, in my terms of visualizing what the problem's supposed to do, that quite possibly is the absolute easiest way to visualize it. I like to write out, okay, these are the number of successes that they're looking for. I literally wrote them out because I needed to visualize, and I marked it up according to the wording of the question, at least 99, but less than 110, meaning, oh, they're not including 110. I love that problem. But like I said, seems like binomials are the types of problems that we do need to practice a bit more, according to the least accurate ones on here. Pay attention to Google Classroom. I am going to be throwing that chi-squared assessment at you either later today or tomorrow. It won't be due Wednesday. It won't be due Wednesday. Trust me on that. You'll have a little bit more time than that. But yeah. If you haven't left a comment in the chat, please make sure that you do so because the bell is going to be ringing in approximately 3 seconds. I was off. That was sad. Anyway. Ooh, I had to do something. Have a good day. You too.